Here's a problem based on 1388 on Mastering Engineering from your homework that I've modified and used in exams in the past. I'd like to show you how you can solve this. So they're asking for forces. You need a free body diagram, and they're asking for forces that act between the path in a double collar and the arm in a double collar. And so the choices are the arm, the path, or the double collar. But if we do the arm, it doesn't help us with the path. We do the path, it doesn't help us with the arm. Plus, both introduce the unknown reaction forces where the arm and the path connect to whatever they connect to. Whereas the collar, one, it's in both questions, and two, will give us the forces that act on the collar without introducing unknown reaction forces from the ground. Alright, so the collar. We need to draw a sketch of the collar, and not a lot of detail is necessary, but I'm going to include enough so that we can identify the parts and use it to help orient the forces. Alright, it's got these two parts. There's the middle, and the radius is aligned with this. Given that this problem is set up with r as a function of theta and theta, polar coordinates are the way to go. Let me switch to blue for the coordinate system. So this is the radial direction, and perpendicular to this, not in line with the path, because the path is not a circular arc, the radius is not constant. So perpendicular but not in line with the path is the u theta direction. With these problems, it's crucial to get those kind of details right. Let me just put in here, this is the path. Alright, so we have the body and the coordinates. Let's draw some forces. First off, they tell us that they give us the weight, and they tell us that this is in a vertical plane. So that means weight will be acting downward like this, and we'll call this W. You could call it mg, but they don't give us mg. The weight equals 9 pounds, which equals mg, which equals the mass times 32.2 feet per second squared. And then we have reaction forces from the rod. That's going to be perpendicular to the rod. I'm going to draw that like this. And I'm just going to, they call it an arm. I'm going to call it A for arm. And then from the path, that's going to be perpendicular to the path, which is not aligned with the radial direction. So I'm going to put that like this. And here's the path. Alright, so we have considered weight, we've considered contact, we're told it's smooth, so there's no friction, and that should be everything. Next, write the equations of motion. So let me switch back to black. We can sum the forces in, let's do the radial direction first. And we have, alright, so the weight is downward, whereas this is slightly upward. So I'm going to say minus mg, I should put in w, because that's what I'm using. And as I tell everyone in class, there should be a one-to-one correspondence between the symbols on your free body diagram and the symbols in your equations of motion. And the weight doesn't align with either of these axes directly, exactly, but we can see that when theta is at 0 and the radial direction is horizontal, the weight will be completely in the u theta direction. And then when the arm is vertical, the weight will be exactly opposite UR, and the sine function will do that for us. The force of the arm is exactly aligned with the theta direction. It's perpendicular to the radial direction, so that won't show up in here at all. And we will get a component from the normal force from the path, and that is in the radial direction approximately enough, so that's plus p. And then we need to know what is this angle, or how is p oriented with respect to either UR or U theta. And it's not theta. Let me just put theta in here. This is theta, and this is theta, but this angle is not theta. And luckily, if you've read the chapter, you know Hibbeler introduces some technology that'll get us out of this problem. That is that they call this angle right here, specifically from the UR direction, from the radial direction to the tangent to the path, and they call it psi, and they give an expression for psi. Psi equals the inverse tangent of r over dr d theta. And we have an expression for r, so we can calculate that. R equals 0.9 sine theta plus 1.3, and theta is 45 degrees, and when you plug that into your calculator you get 1.9364. And then dr d theta, note that this is not r dot, which is dr dt, this is dr d theta, is simply 0.9 cos theta. And when you plug in theta is 45 degrees, you get 0.6364. And those will be in feet. So we can plug that into here, the 19364 and the 06364, and this gives us 71.807 degrees. So that's right here, 71.807 degrees. And hopefully you can see that P is perpendicular to this collar, and this collar follows the path, and so that's tilted from here. This is the complement of 71, and that is where do I have it? I better calculate it. I think it's 18 something. 90 minus 71.807. 18193. So that's here. 18.193, and that is also here. So this is 18.193 degrees. So for writing the equations, you can either use psi and the correct trig function, or its complement. And in this case, the complement's easier to use in C because we know we're in this direction, and so we want cosine of this. Cos of 18.193 degrees. And those were all the forces. We already decided A was out, and so that equals MAR. And also, actually from chapter 12, we have an expression for AR is R double dot minus R theta dot squared. And so theta dot we're given, that is here. This is theta dot, and R dot, so dr dt equals R dot will be, since we're taking the derivative with respect to time and theta changes with time, we need to use the chain rule here, and we've taken the derivative of the outer function. We need to take the derivative of the inner function, which is theta dot, and so this becomes 0.9 theta dot cos theta. The convention is to put the theta dot in front of the trig function so that without parentheses around the parameter to the trig function, there's no ambiguity. And if you plug in the numbers for this, you get 3.182. And that'll be feet per second. And we need theta double dot. So we take the derivative again. This time we have two functions of theta that are multiplied together, and so we need to use not only the chain rule but also the product rule. And this is going to be 0.9 times, take the derivative of the first one, theta double dot, times the second one, cos theta, and then the derivative of the second one, which is minus sine, and then you have to use the chain rule to get another theta dot. So this will be minus theta dot squared sine theta. And if you plug in the numbers, that turns out to be minus 15.91. And if you take these numbers and plug that all into here, this turns out to be minus 64.3. And so now we can solve for P. P equals MAR, and we have AR. Oh, and we have to do this. That'll be M equals W over G, which is 9 over 32.2, which is some number of slugs. 9 divided by 32.2. That is 0.2795 slugs. And we can add W sine theta and divide the whole thing by cos 18.193, and you should get minus 12.2 pounds. So that's one thing. Oh, this first question is this number. And then we get one more equation of motion because we have two coordinate axes. So sum of the forces in the theta direction. Well, right off the bat we have A, and we're also subtracting the weight this time times cos theta, and we're subtracting a component of P minus P sine 18.193 degrees, and that equals MA theta, and we have an expression for A theta, which is R theta double dot plus 2 R dot. That's supposed to be an R dot. R dot theta dot. And we have all these numbers, plug them in, and this turns out to be 31.8. And that would be feet per second squared, as was this, feet per second squared. And we can solve this for A. Will be simply M A theta plus W cos theta plus P sine, I'll do 90 minus psi. And we have numbers for all of these, and that turns out to be 11.4 pounds, which is the third answer necessary. And that's it. So, free body diagram, equations of motion, and if necessary, some kinematics. Okay.